Hi, Albert here. In the last two videos, we've seen what it means for a shape to be symmetric. It means there exists an isometry such that after application the shape looks exactly the same as it did before. We've also seen what it means for two isometries to be the same. It means that under each of the isometries, all of the points in the plane are mapped to the same places. For example, a rotation of 90 degrees clockwise should be considered the same as a rotation of 270 degrees anti-clockwise, because the points of the plane are taken to the same places under each of those transformations. In this video, we're going to move on from looking at individual symmetries of an object, and we're going to consider all of them at once in a handy object known as the group of symmetries. So, what is the group of symmetries? Well, in a basic sense, it's what I just said. It's the set of all of the symmetries of an object. But it's actually more than this, because symmetries are not distant, isolated objects. They interact with each other. To see what I mean, let's look at an example in detail. Let's consider the square and work out what the symmetry group is. We have already seen that the square has both reflective and rotational symmetries. But in fact, there is a symmetry of the square that is even more basic than these two. That's right, the identity symmetry. Even though this symmetry is perhaps less interesting than the others, it is a symmetry nonetheless and deserves a symbol. Let's denote it ID. We'll collect up the symmetries we've found so far using curly braces like this. So how many rotations are there? Well, we can rotate it clockwise by 90 degrees, clockwise by 180 degrees, and clockwise by 270 degrees, and it looks the same, so these are all symmetries. If we rotate another 90 degrees, then in fact this is the same as doing nothing. To see this, let's label two squares on the corners so that we can see whether two isometries have the same effect. This left-hand square is being rotated by 360 degrees, and we'll apply the identity isometry to the right-hand square. We can see that the result is the same, therefore these two isometries are the same and should be considered the same symmetry. What about rotating anti-clockwise? In fact, this is the same as rotating clockwise. Since all of the four corners of the square map to the same place under rotation by 270 degrees clockwise and rotation by 90 degrees anti-clockwise, these isometries must be the same. Okay, so it seems we have only three rotations. Let's label them R90, R180, and R270 to indicate that they are rotations by 90, 180, and 270 degrees clockwise respectively. What about reflections? A little thought shows that these are the only ones, and we label them F1, F2, F3, and F4, where F stands for flip. Okay, so now we have a list of the square's symmetries, but as I mentioned before, there is more to the group of symmetries than just the list. To see this, first we note something very important. Combining two symmetries gives another symmetry. The reason for this is very simple. Consider two symmetries A and B. And let's write the combination of these two symmetries as AB, i.e. the symmetry we get if we do A and then B. Since A is a symmetry, it preserves distances and leaves the square looking the same. Since B is a symmetry, it also preserves distances and leaves the square looking the same. So doing both in a row will clearly preserve distances and leave the square looking the same. So AB is also a symmetry of the square. So what happens if we try and combine the symmetries of the square that we found? For example, if we repeat R90 twice, we're going to get 180. To represent this fact, we write R90 equals R180. Or even R90 squared equals R180. Notice that the square here means do the symmetry twice rather than the usual multiplication of numbers. It's just notation, but it's a very convenient and useful notation, as we will see. Similarly, we have R90 cubed is R270, and we also have R90 to the 4 equals the identity symmetry as we saw earlier. Okay, so we can write our list of symmetries as identity R90, R90 squared, R90 cubed instead of identity R90, R180, R270. Any more simplification? Well, we can't get our reflections by just doing the rotation R90. Let's single out one of our reflections, perhaps F1, which we'll now label F. Let's also simplify our notation by writing R instead of R90. So we can now write the group of symmetries as id R, R squared, R cubed, F, F2, F3, F4. So what about F2, F3, and F4, those other reflections? Can we write them in terms of R and F? It seems unlikely, but let's see what we can do. So we'll start with F. If we combine F with itself in the same way that we tried to combine R with itself, we'll do just a flip twice, and we're going to end up with the identity. So that gives us the equation F squared equals identity. So we're going to have to try and combine these two different symmetries together. For example, we could do F and then R, which will notate FR. What symmetry is this? Let's track it and figure it out. We'll label the corners so that we can see what happens. So here we'll do F, and then we'll do R. And we see that this is actually the same as F2. So we get the equation FR equals F2. You can try other combinations of R and F if you like to see what happens. Pause the video if you want to think about it yourself. Okay, so if we do that, we'll see that if we do F and then R, we get F3. And if we do F and then R and then R and then R again, we get F4. So our collection of symmetries can be written just in terms of F and R. There are other combinations, though, that we haven't tried yet. For example, we could do R first and then F, the symmetry RF. What happens in this case? So if we just try this, do R, and then we do F. Does this look familiar? Yes, I think it looks exactly the same as our F4 from before, what is now labelled FR cubed. So we get the expression FR cubed is equal to RF. So F and R are known as generators for this symmetry group because every single symmetry can be written in terms of F and R. And these three equations here that we've discovered are known as relations, since they describe relationships between the generators. Okay, why did we bother doing all of this? It looks like just a relabeling, right? Well, actually, it has revealed the structure of the group of symmetries to us, how they combine together. As an example of why this is so useful, consider the following symmetry, FR-FR. What symmetry is this? Well, one way we could work it out is that we could draw the square like we have done before and track the corners and see if it's similar to anything that we've noticed before. However, we can now do it differently using our relations. Using relation number 3, we see that FR-FR is actually the same as FR cubed R, using that last relation, replacing the RF in the middle with an FR cubed. And now we can combine the two F's on the left into an F squared and the 4 R's on the right into an R to the 4. Now, using the other two relations, we have that F squared is equal to the identity, and R to the 4 is also equal to the identity. And so this is actually the symmetry that we get if we do the identity and then the identity, which is, of course, just the same as doing the identity once, since it doesn't do anything. So just using algebra, simple algebra, we figured out that this complicated combination of symmetries is just the identity, and it was much easier doing that than to track the corners. Okay, one final thing to talk about before we stop talking about squares, then I promise I'll move on. In the last video, David mentioned that every symmetry has an inverse, i.e. for each symmetry there is a symmetry that undoes it. What are they for these symmetries of the square? Again, the generators and the relations make this easy. By writing all of our symmetries in terms of R and F, it's very clear that R cubed is the inverse of R. Because if we do R cubed and then we do R, that's the same as R to the 4, which is the same as the identity. Similarly, what about the symmetry FR? Well, we've seen that FR-FR is the identity. So in other words, if we do FR and then FR, FR undoes the first FR, so it's actually the inverse of itself. I'll leave it as an exercise for you to figure out what the other inverses are for the other symmetries of the square. So, we've now seen a full example of a symmetry group, and we have a good idea of the kind of properties that they have. Let's record the most important ones here. Symmetry groups always have an identity, a symmetry that does nothing. Symmetry groups always have composition. So if we take any two symmetries A and B, we can always combine them to give another symmetry, AB. Symmetry groups always have inverses, i.e. for every symmetry A, there is a symmetry B such that AB is the identity. Usually mathematicians denote the inverse of A by A to the minus 1 in keeping with the multiplication notation. Mathematicians are very keen on abstraction, and in fact they will tell you that any set which has these three properties is a group, whether it's the symmetry group of a shape or not. For us, however, we will always be working with the symmetries of a specific object or shape. So, when are two symmetry groups the same? In other words, when do two different shapes have the same symmetry group? Consider the following two examples. Pause for a moment and have a think about what the symmetry groups of these two objects look like. How many elements do they have? What are the generators? In fact, both of these shapes have exactly 6 symmetries. So does that mean they have the same symmetry group? No, because they interact in different ways. The first shape on the left has only rotational symmetries, and if we denote the rotation by 60 degrees by capital R, then its symmetry group looks like this. Identity R, R squared, R cubed, R to the 4, R to the 5, and then R to the 6 is the same as the identity, because of rotation by 360 degrees, the identity is the same as 6 rotations of 60 degrees. In other words, it's generated by just one symmetry. Meanwhile, the shape on the right has both rotational and reflectional symmetries. If we denote rotation by 120 degrees clockwise R, little r, and the reflection across the vertical axis by F as before, then its symmetry group looks very similar to that of the square. Identity R, R squared, F, FR, FR squared. So for this one we need 2 generators. Since these symmetries of these two groups interact in different ways, we say that they have different symmetry groups. And we'll say that two shapes have the same symmetry group if we can find generators for each, such that the symmetry group and the relations are identical when written in terms of the generators. As an example, consider this shape. This is different to the shapes above, but it has the same symmetry group as the first one, which is clear if we write the elements in terms of capital R. Alright, that should be enough to be getting on with. If you have any questions about the material here, please let me know or post in the comments. And there are some exercises to try now involving calculating some symmetry groups of your own, including in 3 dimensions. See you next time.